if you remember on Friday, I think my focus was trying to emphasize differences in processing technique. We realized together, I think, that a lot of times if you can get by with raw product, essentially plates, sheets, bars, or even tubes that are made in very large quantity using pretty much continuous processing, that first of all, you get good properties because it's being deformed, and we'll go through the detail of that, but it's also very available, so it tends to be less expensive. Then we started going more into what it meant to cast, that you need to melt the metal, you need to protect it a lot of times so it doesn't oxidize at high temperature. And then you can go to a various range of mold material, and a lot of times you go through this process for a lower price, as opposed to making a complex fitting just out of machining or forging operation, which takes a very high equipment cost. So I'm going to dive a little bit deeper to make sure you all understand a little bit more the behind the scene for casting. I think it will help you not only to understand both wrought product and castings, and also plastic injection molded parts. So I have a lot of kind of basic concepts to go through. I brought a few examples, and hopefully this is fun. I do have a reference. I posted it on our Stellar site. I like this book from Porter and E. Sterling just for the reason it's not super complex. There's a chapter there on solidification that covers most of what we'll go through today. There are other chapters that I'll refer to when we talk about heat treatment that are also well explained into this. It's not meant to be the most complex description. In course 3, we have 321, and this is the book associated with it. It will go through a lot more detail on solidification and what it means to have homogeneous, heterogeneous, and how you calculate what you're going to get out of a process. So I refer to both of those here if you're interested to go deeper. Now, the main idea is if you have a liquid and you're trying to make a solid, and I think that the analogy of snow and ice is a very good one. If you allow this to be a very, very slow process, lots of times you'll have one particular solid that's going to start to form and grow and take a lot of space. So you can see if you have condensation on your window, you'll see this massive grain of ice that is really just one crystal with one orientation. Now, why did that happen? A lot of times it's because you were close to the equilibrium, and therefore it needed some thermal activation, time fluctuation to reach this critical nucleus. And when you got it, then it started to grow quickly and nothing else happened. Now, this is exactly the situation that most casting processes try to avoid. In casting processes, you want to start with, in general, and there's going to be a blade example here that's different, but in general, you want to have as many of those so it's more homogeneous of a microstructure. So one way to essentially avoid having one crystal forming and becoming very large is to cool faster. And I have some basic processes here. So I think you guys see that there is a definite size of a crystal embryo, let's call it. So just the starting point, everything is in the liquid, but at some point in time, they will line up as a crystal just because of random variation, thermal fluctuation. Now, if this embryo is big enough, it'll grow, and that's fine. Typically, if you don't have any mold, any interface, you just have a bulk of liquid, it will take a great increase in your free energy before you start forming the solid. So if you look into a lot of common alloys, and let's focus on iron for this case. We went through last class iron. We'll start to solidify around 1500, 1600 degrees centigrade. And if it's in a bulk and there's no mold, you'll have to cool it down an extra 300 degrees. So now you're only at 1300 degree before you start forming the solid, just because of that critical mass that you need to put together. So that doesn't happen in practice. In practice, you do form solid very quickly, and the main cause for metals is the interaction with the mold. So the mold essentially reduces the volume by a factor of, say, 20 on the amount of material that needs to be all coordinated to form a solid. So I hope this brings in the question, if I have, a sand mold, a metallic mold, a mold that has a special treatment on it, it will affect how I'm going to start the solidification and how good of a part I'm going to get. And this is actually testing I've done myself when I was your age. We had essentially a big process that we were developing, and part of that process required a good understanding on how the mold, a metal mold, would interact with copper in our case. And we had this experiment where, if you were here Friday, I showed some videos, and I think people were lighting up because it was kind of a ugly shop with all the metal, very, very risky kind of color, very hot. It is what happens in a foundry. So you melt the metal. You have to have high protection, wearing fire-resistant clothing, and then we were lowering this essentially sample mold into a molten bath of copper. We were keeping the copper about 20 degrees above the melting point. So because of variation, we didn't want to start to solidify. And by lowering we had a prepared surface. So one side was insulated, one side here was essentially a flat surface, just engaging with the liquid. And you can see that what we were doing is just varying that front surface here that was in contact with the liquid. And we saw a lot of variation in how the product looked like, the solidified product. So if we have a very polished surface, it looked fairly homogeneous. Then we start having a certain roughness. So these are kind of protrusion, thicker deposit. And then somewhere in the middle, these thicker zones got bigger, very big. And then at the end here, we only had two spots where it was very much in contact. Now, there are a lot of things that are interacting here. The first one is how many kind of main crystals I started with. So that does have to do with the shape of the mold. Now, there is another aspect, like in this instance, where if I start to solidify a lot more material in one location, I can essentially start bending my product right away, and I lose contact on the other location. So as soon as you solidifying is one thing for the metal, but then you want to maintain the contact. And that's one advantage with a die casting process, where we're looking at earlier about the big piston, putting the pressure on, is to try to make sure whatever you start forming on the surface stays in contact so it continues being homogeneous. And that's a little bit what we saw in the heat transfer. A lot of our work was to characterize kind of efficiency and what was going on. If it was polished, we were not really getting a very high heat transfer. We didn't have as much surface interacting, and also it was easy for the product to separate from our mold very quickly early on. So we had an increase in the heat transfer with roughness, and this is discussed in our publication. The last data point, so the rougher sample here shows a higher heat transfer, but it's not true because it was only at two spots. So if you weigh this one sample here, it's actually, it had less overall heat transfer. It's just because our sensor was at the location of one of the big bulge. So it looked like we were solidifying a lot, when in reality, it wasn't that much. So all I want you to remember with this is the metals will interact with the mold. That's where it starts. Because the molds are generally cooler, and it allows you to avoid this homogeneous solidification. Then maintaining that contact between the mold and what you're solidifying is really a critical parameter, whether you're going to have homogeneous shapes, whether you're going to have a lot of distortion from the original surface, because if you solidify more in one area, it's going to act stiffer. And everything does want to deform as it's cooling down because of thermal expansion. Okay, so we'll move on to segregation. I showed these images, but I was going a little quickly Friday. These are dendrites. They're very common in casting of metals. There's a variation of them that we're going to go through for polymer just in a few minutes. The reason we're forming them, that's something we discussed. We said the alloy wants to start making the pure metal because it doesn't like to have these extra impurities. So we went through, in the case of aluminum alloy, we said, okay, so we have aluminum here, it's a low melting point. And then if I had silicon, it's this axis, I can reduce even further my melting point, and I have these two faces. It sounds like a good idea. So when I start casting something of this composition, there's something very fundamental going on. You don't have to all remember this, but maybe some of you that were good with thermodynamics will follow what I'm doing here. This is how we draw phase diagrams. All we need to do is look at the free energy, this G, for each phase. So the alpha, the pure aluminum has a certain energy curve as a function of composition. The liquid also has this energy curve as a function of composition, and then the kind of the silicon-rich phase has the same thing. So what you have to do in this is always think that if you remember free energy, you try to minimize it for a system, always. That's what defines your equilibrium. So if I have a composition, say, right in the middle here, and I'm not going to take, this was drawn at the temperature T1, we'll go a little higher. It's the same concept. You kind of, if we go up in temperature, all that happens is these two things goes up, and we don't have this beta phase is just way up. So I'll actually redraw it so we can be very clear, because it looks complicated. I know that. It's so long to say, oh, it's actually not that bad. So we have the alpha, and we have the liquid. Let's just assume this is the only thing we have, and we're looking at our free energy here, and this is our composition. So we'll say percent silicon. Okay, so we had a certain composition. Say it's our eutectic composition. So what happens is, if I stay at that composition and I try to have the liquid at that composition and the solid, the aluminum phase at that composition, this is my energy level. Doesn't look good. So what I decide to do is say, hey, what if I just try to minimize? So this is, a very simple mathematical process of just trying to find a tangent to these two curves and say, all right, that's fine. This is my overall composition. But the way I lower the curve to the maximum is by having my solid with this concentration and the liquid with this concentration. I don't violate any rules here. I do rely on diffusion. So what it means is, to make this one, some of the silicon's going to have to migrate to the other side. And to the extent that you do have the two faces, they'll just grow one respect to the other. So when we start from the liquid, say we're right here, all that needs to happen, because in liquid, diffusion is very easy. There's no problem there. So all you need to happen is start forming a solid that will have less silicon in it, and it will, for the reason that it represents less energy. Now, when you do it, what happens, and probably you can follow this intuitively. I think I'm getting to where I wanted to go. You have to push the silicon into the liquid. So if you are on a flat like this, and you're saying, okay, this is aluminum, and I'm having the silicon go this way. Fine, it will take a while, okay? It's going to happen, but it will take a while. So nature is good. Nature takes the path of least resistance. You say, what if I just push the silicon sideways? So up here, at the very front, it's a lot easier. I don't have that buildup of alloying element, and therefore I can solidify. So it is the main reason why we form dendrites in casting metals. Is you push all the solute element, everything that is not the pure metal, outside the path, and maybe you'll reach a point where, oh, I got some silicon here, and then you form secondary dendrites that go into another direction, and you see that in micrographs. It looks impressive, I think, but you know, it's very common. One thing that the casting shops do when you have that big bullet coming down is they'll have magnetic steering, so they have enough of a magnetic field that's going to break out these dendrites as you casting, and it's going to reduce the amount of segregation by far. So having the dendrites themselves is a big reason for all these variations in composition. There's a lot of calculation you can make to determine whether or not you'll form the dendrites. I don't think we need to go into the details. I'm trying to think. To me, this is the most intuitive and more, you know, long-term remembering. The detail is really shows up right here. Oh, this is useful. So I'm showing here what will happen up above if you took all the time you need to solidify, that you eventually form right here. You form the solid at this concentration and the liquid at this concentration. Everything is good, no problem. Oh, we're actually looking over here. So you respect this diagram, but the reality, the most common reality is when you start to form your solid, say at this temperature T1, you form it at a certain composition, so that's right over here. And as you're going down in temperature, you're supposed to keep increasing that concentration, but because you don't go back to where you started, because essentially you say there's not going to be enough diffusion in the solid, is why you end up with less in average of the alloying element in the solid as opposed to the liquid. If you go a little faster is where it gets more. So this essentially still follow the phase diagram for the liquid. You see that the concentration in the liquid is always constant for the distance. So you end up with essentially a gradation in the amount of alloying element you have in the solid, and then you have your liquid that is much higher concentration. So your liquid would be this eutectic composition right here. It happens, but a lot of times you go so fast that in addition, in the liquid itself, you also have a change in concentration of the impurity. And that's what we were looking at in this diagram. We said, oh, well, we have an extra silicon amount right in front of the solidification front. Okay, fine. So if I have extra silicon, it means that I can optimize my cooling rate and my solidification by keep changing the path that I'm going into. So we call it the constitutional supercooling, and it's this condition of having just enough gradient, and that's what really depends on your cooling rate. And you can calculate it. At the same time, a lot of times you're forced to deal with what you have. We'll go through, yes?
Since you said like supercooling will actually encourage dendrite formation,
Mm-hmm.
but it's not actually which we want all the time. It's not desirable.
Mm-hmm.
So is it like a trade-off kind of thing? How
Yeah.
fast you do it?
And the trade-off in terms of cooling rate and solidification, we see it more in plastics. With metals in general, you want to go the fastest, so you have as many little initiation points. With polymers, it's different because they're so big, the chains, that if you go too fast, you never really get the chance to form a crystal. So that trade-off that you're mentioning about comes very useful. For the diffusion, that is very true. So if you want to avoid the segregation part, this supercooling aspect, then you don't want to go too fast. There's going to be a certain rate where you won't form it, and you'll still be solidifying. Because that is essentially allowing enough diffusion in the liquid. If you allow the diffusion in the liquid, then you don't form the dendrite. All right, we reached the most complex level. Now let's go back to something a little easier. If you try to make the largest quantity of wrought product at the lowest cost, and I'm going to take a very specific example. You want to make aluminum foil for the food industry. Very thin, right? You could start with the big bullet that we talked about, maybe a foot by a foot, or you can make it 3 foot by a foot. But the energy and the equipment involved to bring it down to, some millimeter thickness would be extremely large. So there's been effort for the past 50 years in terms of reducing the size of the first casting you make. And the strip caster is one of them. It works very well for aluminum because aluminum has a low melting point, a high conductivity, so it's relatively easy to control the process. It's still under development for steel. I worked on that, and one of the issues is because the temperatures are so high and you have less thermal conductivity, it's very hard. So the strip casting is these two wheels going on, and then you have essentially boundaries on each end to contain the liquid metal. The good aspect of it is you can, by controlling the cooling on those rolls and their surface characteristic, you can really tailor how fast or slow you start forming the shell of solid here. But one difficulty is when this side and this side meet to form the actual solid is how do they match? If they don't match, then the pool starts fluctuating, you start having more solidification here, and the process is not in control. So it's a very, very delicate balance. You can see the advantage is, first of all, you don't really have a mold. All you have is two rolls. So you can really control their cooling. You don't have a lot of wear. You don't need to push things. They just get self-driven. But what becomes really important, and that's the reason I was doing the research I was doing, is you want those two halves to come together and bond to make your product in the end. Now, you still need to do some hot forming, but if you start with a plate that's only ½ an inch as opposed to a foot thick, it's a lot less expensive to bring it down to a millimeter thickness. So they're a great economical incentive to really understand and improve casting processes. Yes?
What are like the minimum thickness levels achieved in this case?
For this strip, For us, it was half an inch. It's really, well, I mean, we may have done 3/8 once. We had trouble where just because then it's coming out here and you have to turn it. So one of our difficulty in our testing was to cool it enough to be able to turn it. So, but we were not as concerned. So it was kind of sometimes breaking down in pieces. And that's why we didn't want to make it too thin. You could, for aluminum, I think they were going a little thinner than that, than a half an inch. And the aluminum was kind of a commercial equivalent, with the main difference is everything is lower temperature, higher conductivity, everything just is easier. So that's the type of thickness that you're looking at. Now you can make amorphous metals using a very similar process here, but then you make them very, very thin. So I don't mean for this to be like, oh, this is the only thing you can do. If you want to do a bulk metallic glass, this is a very attractive way to do it, because you bring in as much cooling as you want, and yes, you can make that spacing much thinner.
So in a way, it's very suitable for amorphous materials.
Yeah.
You can get as thin as, I guess.
Well, much thinner than what I've done. I don't know that. I'm sure there are limitations as well. And it's not because you start as a plate that you have to worry. If you want to make a round bar, that's fine. You just roll it into that geometry very gradually, and that really isn't a problem. Any other questions on certification? We talked about the die casting. That's the one where when you inject the metal liquid, you pressurize, so you keep the contact with the surface. I wanted to throw in for you a variation of it that is done commercially quite a bit for aluminum, which is instead of injecting a liquid, you can inject a mixture of solid and liquid. So instead of forming the dendrites and everything in terms of having a very heterogeneous microstructure, you can have these solid particles that are very deformable, that are essentially your feedstock into the mold. So you're kind of making a composite, but it is metal faced, and therefore it will provide you your ductility, for example. It's probably the past 15, 20 years been pushed forward quite a bit. And for the reason we discussed, we don't really want to have all these dendrites and that segregation. These are paths for low ductility. So it's a way to avoid them very rapidly. We made a little bit of a bridge last time talking about polymers. I said, I'm looking at the die casting machine, and I'm thinking, well, this is kind of an injection molding machine. So I wanted to take some time here to go over with you some similarities in how we process polymers as opposed to metals. Well, we typically, with plastics, and I'm thinking thermoplastic. I'm not going to do the epoxy thermoset right now, but say we take polyethylene. That's a very large volume material. Polycarbonate, polypropylene. These types, we have nylon, things that we make a lot of engineering product, not necessarily super reliable product, but all of these except the polycarbonate are semi-crystalline. And that makes a big difference when we talk about how they get cast. But before we go there, let's talk about how you make these parts. Typically, you start with pellets, just a little bit like you start with scrap or raw iron for making steel products. You have these pellets, and they go into these heating system. It's essentially deformed and shear. to heat it up until it is melted. So it's above the fusion temperature, and at that point, when it's gone through all the screw system to heat it up, you can inject it into the mold. Now, one main difference, when the polymer gets into the mold, you still have the surface effects. Say we're making something that's elongated here, and we're injecting, I don't know, we can inject from top and bottom. It's going to flow in here, and then maybe make an interface in the middle right here. So you fill the space, and you're going to start forming some crystals on the surface, right? Because it's cooler. But in general, with the plastics, the crystals don't really grow as dendrites. And you can probably follow that with intuition. If I'm trying to take a big pile of spaghetti, and I'm really, because that's what it is, and I'm trying to put some organization in them, and I start on one side, I'll make some organization, that's great. But I get to a point where everything else is so tangled that that's it. That's all I can do. And that's why we call them semi-crystalline, because it's almost impossible to crystallize all of it. There's always going to be some faces that are not crystallized. So I'm showing this here. This is called a spherulite. Yeah. Make sure I got this right. And we'll go back to this in deformation processing. I'm very, very pleased that I can tie the both of them. This is new this semester. And you can ask me questions if I'm trying to go too fast or too slow. Say, speed up a little bit. So you start right here in the middle, and the concept of forming a spherulite is you do manage to make some folding of chains to get them in a real crystal structure. A very strong relationship between the molecules from one plane to the next one. Now, all that extra material, you have to do something with it, and it goes into the amorphous zone between these crystallites. So even though we start at one point, we really do grow, if we can, in all directions, or if this point was at a mole, it's going to be half a full sphere. And we're going to go as far as we can. So what really defines the rod quality or the original quality of this injection molded part is how many of these nucleation sites you had, because they'll grow until the next one meets with it. So when you look at this microstructure as cast here, what you want to see is just a bunch of spherulite next to each other. And ideally, in my opinion, you don't want them to be too big. So this would be the example where I get very worried, because the bigger I go between them, the more I'll see the effect of having something very, very stiff with something very soft next to it. And that's going to affect my deformation a lot.
The ones which are like kind of flexible and all must be having smaller ones, small spherulites.
Yes. So I brought this here because we didn't talk about plastic last time. Plastic pipes, a lot of times, are extruded. So I don't want you to think that it has these spherulites. It does get deformed as well. So you do need to optimize to be in a good range, but ultimately you're going to break down that structure anyway. All you want is not damage the microstructure while you're doing that. Yes?
So all those, the nucleation sites for spherulites form very quickly on the edges. Is that what explains the skin strength, added skin strength in injection molding?
It's one aspect.
Okay.
The main aspect of the skin effect in injection molding, I'm glad you're pointing it out, is the flow, because essentially I am having a shear flow going on between my mold and the bulk that's getting shifted here, and that's going to orient the molecules themselves. So it's not just a direct effect of how many crystallites you have. It's you don't form crystallites as easily because now everything is kind of stretched. So and it does have much better properties. So sometimes I forget to mention some of this. So if you take an injection molded part and you machine it to make it better in terms of accuracy, a lot of times you will lose strength because you're losing that orientation effect on the surface. Now there's another thing I mentioned. I said, well, we're going to break down these ferrites. That is if we do an extrusion after the fact. If all we do is injection molding, that's it. That's all you get. So you do want to have that skin. The problem is it's never get as good in certain corners. It's going to vary, so you cannot necessarily rely on it that much. But if you are in the middle of the part and you have bending stresses here, the first thing you don't want an injection molded port where you have high stresses. So you need to be in an area where you know that you will be gaining an advantage. And the worst is to be at the mold line where you have two injection ports that meet. It's a very common and complex part to have multiple injection points. So where everything meets, the polymer from one side doesn't really entangle itself as well with the polymer on the other side, and you got a much lower long-term strain. All right. So it's different because now we're dealing with a different process here of forming our solid. This polymer certification doesn't really tend itself to issues of segregation, except that between the dendrites, you can have a little bit more of the impurities. What I'll say to counteract that is, say you have, and sometimes you do that, you put a nucleation agent, so you put very, very small particle that will be the center of your spherulites. So because they're big enough, they're not going to end up in the corner because they are the origin of why you had the nucleation. And that's the same process of heterogeneous nucleation where you start from something as opposed to having to build up from scratch. Well, you guys seem interested. Anything else on polymers? Because I was going to move to deformation now. So now is a good time if there's anything else. And you can always go back. Oh, I want to distribute this one. This is a selector, a grain selector for forming turbine blades. It's mostly used for single blades. So here we have a cluster of blades. Not the best example, but that's what I had in my office. So the bigger blades for the turbine side of the engine is typically a single crystal of metal. Now, that's great, but didn't we just say, metals try to make different crystals, different orientation, all that? It's a very high alloy content, so it will want to make dendrites and all sorts of things if you didn't specifically control. So the way it's controlled, the main way it's controlled is you put the entire liquid in the mold at high temperature, and then you gradually cool from one end towards the other end to make the part. It's very expensive. At the very beginning here is where you start a normal certification. What happens is, it gets chilled, it gets cooler, and maybe I have 10 or 20 grains that are growing here. The one that's oriented with the better heat transfer is going to grow faster. And that's a specific crystallographic orientation that allows it for a certain thermal gradient to grow faster than the other. And as it goes through this spiral, in the end, there's only one winner. And it's the one that was growing the fastest. So what you need to do from that point on is to keep it slow enough that you don't get into the super cooling, or that you don't get into enough of a gradient that a little particle in the mold is going to make a reinitiation. That would be really bad. Now, they do need to do a lot of process control and quality control to verify that they have it, but it's, in terms of concept, it's fairly simple. The implementation, though, it makes this process very expensive. I can circulate them around. They're hollow, so it is nothing easy about this, but it's worth it to make them single grains for creep resistance, for resistance to deformation at high temperature. Essentially, if you have a lot of grains at high temperature, they can slide one another. They can essentially, you have diffusion going between the grains. But if it's just a single crystal, everything that to change the geometry has to simply involve deformation within that grain, which is a higher energy process and a slower process than going along the grain boundaries and doing other processes. Okay, so both for metals and plastics, I want you to think about deformation in two different ways. Just to make sure we're all on the same page, because we have people with different background, and I've seen so many, confusion sometimes about this. So elasticity, you have to think of it as something that is a stretch of the atom to atom bond. Most metals and polymers are very, very strong to changing that atomic distance. The molecular distance, a little easier, but these processes don't involve really atoms moving around. They just stay in the same configuration. It's reversible and act like a spring. Everything that we will talk about Friday in deformation processing for both the metals and the plastic is what we call plasticity. So in plasticity, the main difference is the atoms, they do move. So if you look at the landscape, I had A, B, C, everything in there, there's going to be something different about it. It's not reversible, although the concept of reversibility for polymer is really ambiguous. The reason I say so is when we're talking about these ferrolites and all of this, if I stretch everything here, I'm still maintain a certain history of the chains as they were originally. So if I heat it up and allow everything to come back to kind of a more contracted zone, I have a memory effect. And it's typically not a complete memory effect, but it's not as black and white as it is for metals. The metals, they have no idea where they were before you formed them, and therefore they won't have this kind of spring back to a certain type of shape, but the polymers will. So and we could call those viscoplasticity. Plasticity can happen in parts. So what said something really good about steel? I said it's easy to join and it's not expensive. Well, there's something else. Steel is very tough in the general sense that if you take it and you bend it, it will give a little bit. It will deform before it breaks. And that's a characteristic that is used sometimes, say, if you have a bolt hole or if you have a stress concentration in a part in that local area, you can reach plasticity in service. So the idea that it's just for forming isn't true, but we're going to talk about it mostly in the context of forming here. Don't want to make you too worried here. It's just how you define the atomic distance as attractive force and repulsion forces. And perhaps the only thing that I'd like you to keep in mind, there's always a reason why we keep some of these concepts together. Here is the net energy. So when you define the spacing between atoms on iron, for example, it's essentially the lowest energy on that red curve. But what you can see is that it's not symmetrical. In other words, the increase in energy by getting a little wider is not as much as getting a little narrower. And that's why this is the main The simplest explanation why, as you heat up metals, they expand. They expand because then you go a little bit above this with your thermal energy, and you start for a little more energy, you start fluctuating over an average that is slightly bigger. There's nothing there's nothing fundamental that would require the atoms to get further, except that as you go up in energy, that the curve that is the repulsion curve is the one that doesn't require a higher increase, so the spacing does go up. So that would be it for the elastic. And the plastic is probably, I'll ask the question so we'll find out. You take a sample and you deform it. So that's our stress strain curve here. This is essentially the load applied and the elongation. When you do that, you do go through a peak, and then the load's going down. So hands up if you think that this means that the material is getting weaker when you reach a certain amount of strain. Okay, why? The area is changing locally, right? So you have the necking that's starting to form, and you cannot believe, well, maybe it's not course 2 people, maybe it's course 1 people that I see this mistake all the time. Cannot believe how many times I've seen people having trouble with this. So we do the test, and what we found here at a certain load P, and this is just L, or delta L, the elongation, we reach this maximum. And what happens then is the deformation is localizing over a smaller cross-section, but still the same load. And that's why when we plot this, the graph continues, and you see the break right here. I'll tell you what the significance of this here, the significance of the peak, it's not the ultimate strain. It's the ultimate tensile strain. It does happen in tension, but it's an artifact because if you decide, so that's P over A0, but if you decide to keep track of the instantaneous area here, what you'll find is this point ends up with, quite a slope here. So this is P divided by the actual area. It's correcting for the fact that you're reducing in size. And what it means, only when you get to this point, it means that you don't have enough hardening in the material to keep everything deforming at the same rate. So essentially, before we reach that critical point, if I start having one region of my length of the sample that's deforming a little bit more, it's also increasing the strength enough that it stops deforming there and it deforms into another area. So we call that the tensile instability. And the main aspect in terms of deformation processing is I want you to keep in mind, this keeps going up. Now, does it go up indefinitely? Not exactly. So at cold temperature, you can get perhaps 200% strain. So when you reach a deformation factor of about 2, you don't really have that much strain hardening anymore. But it's the type of number that we're looking at as opposed to this here being, this is typically just 15% strain. So there's a limited ability to collect the information beyond that. But if you did, you'll realize that, yeah, there's more resistance always into the metal to deform. Just briefly for the plastics, they show the same. Just do right here. So the plastic, if you pull on it, a lot of times it's going to look just like this. It goes through a peak, then it's reducing quite a bit, and depending on the material, it can either break or go back up. And when we go through the details of this, we'll see it has to do with these ferrolites. So from here to going back down, you're just breaking your spherolite, and then eventually here, you're starting to reorient. So There is, if you are to plot this behavior of the polymer on a screw stress through strain, it kind of levels down. It's not. It will be something like this, and it will have more hardening later. Whether I think it's always positive, but it's very low, and that's why the neck is so pronounced. You're looking here. If you start with the sample, you see it's going to thin down by a factor of half in one area, and then that region stretches, and you end up with 600% strain in your thermoplastic. So it's just what happens. It's the same process. So we'll take it from here on Friday and really go into how we make useful wrought products. Thank you. Including pipes.